Welcome to The Explainer. Today we're taking a truly fascinating journey straight into the architecture of reality itself. We're going to explore a mind-bending concept that translates a highly dense mathematical physics document into this incredibly compelling story of scientific evolution. We're looking at a theory that doesn't just try to simulate physics inside spacetime, but actually asks if spacetime itself emerges from computation. It's a story about massive ideas for sure, but even more importantly, it's about how a single, insightful question from a complete outsider forced an entire theoretical framework to become rigorously defensible.
Okay, let's start with a massive what if. What if gravity, matter, and the very dimensions of our universe aren't simply inputs that were just there from the start? What if instead they're actually outputs? Specifically, outputs of how information flows through a huge, structurally defective computational matrix. This is the radical premise behind Adaptive Computational Spacetime, or ACS. It completely flips our standard view of physics upside down, suggesting that the fabric of our universe is born from a discrete network of causal relationships. To really unpack this, we've got 5 key areas to cover today. First, spacetime as a matrix. Second, transients, feature, not bug. Third, the granularity question. Fourth, the Jim Whitney effect. And finally, making spacetime falsifiable. All right, let's jump right into our first section and look at the foundation, spacetime as a matrix.
At the absolute core of ACS is a single, massive mathematical object called matrix B. It's built by basically sprinkling points into spacetime, sorting them by time, and causally connecting them. And this is crucial because it natively creates a lower triangular matrix, meaning it doesn't silently discard any physics by artificially truncating data. This matrix is made of 2 parts. First, you have D, which is a highly stable anchor point. Second, there's N, a massive nilpotent matrix, which is essentially this enormous grid with over 2 million active non-zero connections.
Now, take a look at this number, 715. It's incredibly important. In linear algebra, this is known as the kernel dimension of that massive matrix N we just talked about. But what does that actually mean for spacetime? Well, it effectively falsifies the naive idea that this matrix just behaves as one simple, single block. Instead, it means the causal set actually fragments into 715 independent, parallel, dynamic channels. Just imagine the flow of time and information literally splitting into hundreds of separate memory channels simultaneously.
Which brings us right to our next section. Transients as a feature, not a bug. Let's see how this matrix behaves dynamically. Because our matrix is highly non-normal, it doesn't just sit there stably. When an input is run through it, we see this incredible explosion in what's called the transient cascade index. Look at this. It starts at a multiplier of 1, leaps to 125, jumps to over 5,000, and then hits a massive peak of nearly 19,000 times amplification at step 3. And after that immense peak, it rapidly decays down to almost 0, showing a fading memory, kind of like an echo state reservoir in computing. So here's the kicker. In most mathematical models, an explosion like an 18,000 times multiplier is a glitch, right? An error. But in ACS, this mathematical explosion isn't a glitch at all. If the theory is right, this transient amplification might literally be the source of our universe's physics. The localization of that massive transient energy could be what we actually perceive as matter, and the eventual decay of that transient could represent dark energy. It is an absolutely breathtaking interpretation of the math.
But hold on, because there was a massive vulnerability lurking in the background here, a mathematical blind spot. You see, for complex fields of numbers, that beautiful 18,000 times peak was clear as day. But for real-valued fields, the math suggested the peak might completely vanish, meaning the entire phenomenon could just be a single seed artifact, just a fluke of the specific numbers they chose for their test, rather than an actual universal law of spacetime.
And that brings us to a huge turning point for ACS, Section 3, the granularity question. This is where the story gets really fascinating. Dr. Jim Whitney, an engineer who specializes in tracking, was reviewing the theory. He looked at it from a totally different angle and asked a foundational question. When you sample something discrete, is there an interval so small that it basically acts continuous? He brought up particle filters, which are a tracking tool used in engineering to manage uncertainty. And by doing that, he fundamentally challenged the project's entire set of assumptions about how they were bridging discrete computation and continuous time. So let's look at how that single quote triggered a total paradigm shift in the framework. Section 4, the Jim Whitney Effect. The research team actually formally defined this as the Jim Whitney Effect. And just to be clear, this isn't about Dr. Whitney swooping in to steal credit. It's about his vital insight forcing the team to rigorously manage their uncertainty. Because of his question, the team realized they couldn't just rely on standard matrix spectrum behavior to bridge the gap to continuous space-time. They had to govern the transition using highly rigorous criteria, specifically pseudospectrum and sequential Monte Carlo collapse, to ensure the math wasn't just playing tricks on them.
If you compare the before and after, the impact is night and day. Before Dr. Whitney's question, ACS was this mix of computed facts and wild speculation about black holes. It was vulnerable to single-seed flukes and ran a real risk of just being dismissed as mathematical numerology. After his insight, the project evolved into a rigorously governed research program. It adopted strict boundaries, used particle filters to govern the data flow, and most importantly, it became completely falsifiable.
Which leads us perfectly into our final section today, how exactly they built a fortress around these insights. Section 5, making space-time falsifiable. The result of this whole paradigm shift was the V20.2 governance document. This completely transformed ACS from a speculative brainstorming notebook into a strict, tiered system of scientific rules. They implemented blocking prerequisites, an evidence ledger, confidence tiers to separate actual numerical proof from educated guesses, and strict numerology firewalls to completely prevent confirmation bias. Let's look a bit closer at one of those rules, the gate zero blocking prerequisite. This is a non-negotiable rule. It ensures that if that massive 18,000 times transient peak isn't a universal phenomenon across multiple random seeds, specifically if it's absent more than 60% of the time, then the speculative tiers of the theory are completely shut down. It literally forces the researchers to prove the math isn't just a one-off fluke before they're even allowed to talk about stuff like dark energy or matter.
And in true Popperian science fashion, meaning science that proves itself by actively trying to prove itself wrong, they created a falsification register. They pre-registered exactly what mathematical conditions would kill each of their hypotheses. For example, if random matrices reproduce those 715 channels, then the idea that those channels represent degrees of matter is instantly dead. They basically built the weapons to destroy their own theory, which, ironically, is the absolute best way to make it truly strong.
Now, this rigorous governance directly dictated how they published, too. Instead of dropping one massive, easily attacked theory of everything, they were forced to break it down into 4 modular papers. Papers 1 through 3 are strictly about the math, geometry, and dynamics. Paper 4, the interpretations paper that deals with the actual physics, is strictly parked. It's locked away until the underlying mathematical foundation in the first 3 papers is absolutely bulletproof.
So as we wrap up this explainer, I want to leave you with this final thought. The Jim Whitney effect showed us that the best scientific questions don't just ask for answers, they actually force us to manage our uncertainty. If building spacetime out of pure computation actually succeeds, simply because a tracking engineer looked at it and forced it to be testable, what other monumental universe-building theories are out there right now, just waiting for the exact right question to make them real? Thank you so much for exploring this fascinating framework with me today. Keep asking those foundational questions.